Hello friends, welcome to section 4 of the Hard Surface Modeling series. This section will be a little different, focusing less on new tools and more on learning good habits and rules when working with the Crease Plus subdivision workflow. The first rule of this workflow is not to let the subdivision modifier determine the shape or curvature of your mesh. This is an issue because when it comes to texturing and texture baking, especially if you are baking normal maps, the high detail mesh that you would be baking from would actually have a different shape to the low detail mesh, causing issues to the mapping and shading of textures. The whole point of using supporting loops and creases is to control the subdivision modifier, but if we are letting the subdivision have control over our mesh, the point is lost and we are back to square one. Over here I have two shapes. Each one is wrongfully depending on the subdivision modifier to curve its sharp edges. This first mesh is dependent on the subdivision modifier to curve its corners. As you can see, the base mesh corners are sharp, but the subdivided result is smooth. We discussed in the last video why we can't just apply a crease to these specific edges. Now let's discuss how to solve it. The answer is quite simple. If you want this edge to be smooth, smooth it manually instead of depending on the subdivision modifier. So let's take each of these edge loops and bevel them using two segments and a shape of 0.5. If this model had more detail, using a stronger bevel with 4, 6, 8 or any even number of edges would be more appropriate. Now, the modifier doesn't change the shape of our original mesh, it only smoothens it. However, we will have to recalculate the circular hole, as the extra edges made them uneven. Select every circular loop and run the circle tool on all of them at once. This model is fixed, let's move on to the second one. In the next section, we will learn about localizing topology, which is a method that will be very useful when working on these kinds of problems in the context of a more complex mesh. This model has a similar issue. These original edges are sharp, but the subdivision modifier curves them. In this case, if we wanted to keep the edges sharp, it would be as simple as creasing them, but let's assume we want them to be curved. In the same way as the previous model, all we need to do is bevel the edges manually, providing a lower polycurved mesh that our subdivision smooths over, instead of completely changing its shape. Notice how for both examples, after adding beveled edges, the difference between the subdivided and unsubdivided models is less pronounced, meaning we have done a good job at controlling the subdivision's effect on our mesh. A good habit is to disable the edit mode view on the subdivision modifier. This forces you to make good base meshes regardless of the subdivided result, and helps you avoid depending on the modifier to determine the shape and curvature of our base mesh. So to summarize, the core of Rule 1 is to be in control of the subdivision by manually adding curvature, and using the subdivision to smooth it, but not define its shape. The second rule is to make sure your creased edges have good edge flow, meaning they are neighbored by two identical edges, and that their flow is not disrupted by poles. Without this, your objects won't smooth well. Take a look at this object. The circular hole is great, our creased edges have good neighbors, and all the poles that would have disrupted this loop have been pushed inwards using another loop cut. However, looking at the outer loops, this one does not have good neighbors, as does this one, which I can select using Alt-click, a red flag, signaling that we have poles at each corner. This is a simple fix. This edge needs a bevel, removing the unnecessary loop and reassigning creases, and now it has good neighbors. For the back loop, you could bevel it the same way and remove the unnecessary loop, or you could insert these faces, creating the good neighbor without also creating an unnecessary loop, making our workflow slightly faster. The poles have also been moved from the corner vertices into the neighboring loop, in the same way as it did with this circular area. In this example, having good edge flow may seem simple, but do not be fooled, this gets much harder to deal with as the shapes get more intricate. Take a look at this shape. Notice how I'm utilizing the first rule, creating curvature manually and letting the subdivision smooth it, and how I'm utilizing the second rule, giving each creased edge good neighbors. We know that only the original creased edges need good neighbors, but in the next section we will look a bit further into scenarios in which it is important to direct the edge flow of other areas in a model. In studio settings, having good edge flow is essential, not only to ensure good shading, but when multiple people are working on a mesh, having the creased loops be easily selectable is a must. Lastly, this applies to all the topics discussed in this section, but for this rule specifically, the only way to get fluent at it is through practice. There is only so much you can learn by listening to me explain it. The third rule is not to be afraid to apply a level or two of subdivision if you don't have enough general geometry in your mesh, saving backups in the process. I know from personal experience, and from others, that it is easy to get frustrated whilst working on subdivision meshes, as you might be lacking geometry to add necessary details, but don't want to add more geometry because it disrupts the shape and smoothness of your mesh when subdivided. In these scenarios, it is always a good idea to have a deactivated collection where you can store a duplicated backup of your mesh before applying modifiers. For example, I have this object, which has a decent amount of faces, but I want to cut a really intricate shape into it, which this object does not have enough geometry to support. Looking at it in wireframe view, with the optimal display option disabled, I can see a preview of how dense this object will be when subdivided. If I am happy with the level of detail I am previewing, what I can do is duplicate this object, press M and move it to a new collection, which I can call backups. Then I can disable this collection and put it in the appropriate collection, in this case within the Rule 3 collection. After this, I am able to take this mesh, apply the subdivision, and create the intricately shaped cut through it. If I ever want to revert back to the unsubdivided mesh, I have that option in the backup collection. The implication of the second rule is not to be afraid of adopting a destructive subdivision workflow at times when you are lacking the required geometry for your mesh, and that applying a subdivision layer is almost always more efficient and effective than flooding your mesh with more loop cuts in an attempt to make it more dense. If you are unsure on a larger scale about a change you are about to make to an entire project, don't hesitate to save a backup. The fourth rule is to always keep in mind the limits of the Crease Plus subdivision workflow. While it is the best way to achieve clean, smooth models, it can be laborious and time-consuming. To confront this, subdivision modelers are required to be able to optimize their workflow, think ahead, and be smart about how they spend their time. The best ways to optimize your workflow is to use non-destructive tools and modifiers, like mirrors, arrays, and instances. Let's go through how each of these can be used. 1. Mirrors, a quick way to generate a lot of detail. You can create, for instance, a small robotic part, and set an empty plane as the mirrored axis, generating double as much detail in half the time. This gets exponentially more intricate once you introduce three-dimensional depth into your objects, and even more so when you add holes on the mirrored axis, giving the illusion of extreme detail. 2. Arrays, another great way to build more complex objects out of one base mesh, generating linear, radial, or even curve-based detail on grids, cylindrical patterns, and curves. To really sell the idea that arrayed meshes are actually larger intricate objects, it is important to implement patterns that flow between instances when arrayed. The more intricate the patterns, the harder it is to spot that this is an array of instanced objects, rather than one detailed object. Making linear arrays is straightforward, cylindrical arrays are slightly more complex. Create an empty plane and a cylinder. Make sure the array modifier is set to object and select the plane. It is essential that they have the same origin. A little bit of maths is needed to understand this, but otherwise it is simple. For any number of faces a cylinder has, pick a pair of factors for it. For example, this cylinder has 32 faces, so I can pick the pairs 1 and 32, 2 and 16, 4 and 8. Pick a pair of multiples, choose one number to be the amount of times you want the pattern to repeat, let's call it P for pattern, and the other becomes the number of times you array the pattern, let's call it A for array. I'll go with 4 and 8, and we'll make a pattern with 8 faces, so P equals 8, then array it 4 times, so A equals 4. I'll select 8 faces and delete the rest, and change the array count to 4. Nothing has happened, because we need to rotate the empty to see the array. To know how much to rotate the array, take the value of A, for in this case, and divide 360 degrees by it. In this case that is 90 degrees, and as you can see, if I rotate the empty by 90 on the Z-axis, our cylindrical array is perfect. Finally, enable the merge option, and the first and last copies option, so that our arrayed objects merge together. I can now edit 1/4 of the mesh, and the pattern is repeated on the other 3/4. Practice this if you still aren't confident in using the formula. We will be learning about curves and arraying along curves in a future section. 3. Instances. Using instances has many benefits. It allows you to model repeating patterns very fast, can help you model parts that are placed with awkward rotations, and using them is less intensive on your machine than using duplicates. You can even stack these optimization techniques. For example, an object can be mirrored and then arrayed, or arrayed twice, or even mirrored and arrayed multiple times. And paired with even more modifiers like the solidify or simple deform, which you could also stack, the potential effects are insane. This not only hugely speeds up your workflow, but also introduces patterns and repeating shapes in your hard surface designs. The fifth and final rule is to plan your topology well. As mentioned near the end of the last section, as we progress through the series, and our knowledge of techniques and tools grows, the need for preparation when working on models will become more apparent. Having a digital or traditional paper where you can sketch out ideas in real time is hugely beneficial, especially with hard surface modeling, where you are imagining complex mechanical systems. Of course, it is important to have reference boards or even 2D model sketches, but a paper you can use to improvise ideas in real time can inspire creativity and help clear frustrations. Let's end this section with an overview of the 5 rules. 1. You must control the curvature and shape of your mesh manually, allowing the subdivision modifier to only smooth, not dictate shape. 2. Good edge flow is essential in hard surface models. Learn to recognize scenarios in which edge loops need good neighbors and poles need to be moved to safe areas. 3. Adopting a semi-destructive workflow by applying levels of subdivision is in many cases the most efficient and precise way to model hard surface detail. 4. Using optimization tools and techniques is a staple of this workflow. Without them, the workflow becomes unimaginably laborious and can become computer-intensive. 5. Spending time collecting or making references, whether you have made a reference board or are sketching in real time, whether it is done digitally or traditionally, will inevitably speed up your workflow, allow you to create more intricate designs, and helps avoid the frustrations. Over time this will become second nature, but for now, it is important that you build up these good habits and practice with these tools, as this will make the journey going forwards much smoother. In the next section, we will be looking at an advanced modeling technique, localizing topology, which is a method used to add geometry to specific parts of models, without needing to add loops that wrap around entire meshes. See you there. Remember to like and subscribe for more, and comment any thoughts or questions.